Okay, welcome back, class. And today we're going to start chapter 3. And chapter 3 is all about polynomials and rational functions. So we've talked about polynomials before at the beginning of the semester. So this is all about polynomial and rational functions. So we've talked about a little bit about these. So now we're going to dive in a little deeper into that understanding. So we're going to talk about polynomial functions, quadratic functions. Well, we talked about polynomials in credit, so we know what these are. But now we're going to talk about it in the context of a function. So polynomial functions, quadratic functions, graphing techniques specific for those, completing the square, a technique for that's also used in graphing. And then we're going to look at the vertex formula, okay, and quadratic models. So let's get to it. So a polynomial function, again, we have our polynomial expression here, right? Algebraic expression of a polynomial, and then we saying it's a function. So polynomial function f of degree n, where n is the non-negative integer, is given by this equation. Okay, again, a sub n times x to the nth power all the way down to the constant term. So we have where an minus 1 all the way to a1 and a0 are real numbers, where a sub n is not equal to 0. Otherwise, if it was equal to 0, we wouldn't have an nth degree polynomial function. Okay. So again, just a little bit of review. Polynomial functions, we have this one. This is a constant function, degree 0. Leading coefficient here is 2, okay, which is also the constant term. Here we have a linear function, has a degree 1, and in this case the leading coefficient is 5. Here the leading coefficient is 4, and the degree is 2. This is a quadratic. Then we have a cubic function, which has degree 3 with a leading coefficient of 2, and then here we have a quartic, is degree 4, leading coefficient in this case is 1. And so a quadratic function has a degree 2. Okay, so a quadratic function has a quadratic equation or quadratic expression. So it has a degree of 2 with a leading coefficient of a not equal to 0, where a, b, and c are real numbers. The simplest quadratic, as you would imagine, is our basic function, our basic squared function, x squared. So all polynomial functions stem from this one. Okay, and so again, we know that these are all parabolas. And in this case here, we have a domain of all real numbers, and we have a range of all non-negative y values is the range. Okay, so 0 to infinity for the range. The domain is negative infinity to positive infinity. Okay, a couple of things. Parabolas, they all have an axis of symmetry. They're all symmetric with respect to some line. And again, that line is called the axis of symmetry, or axis for short. And the point where the axis intersects the parabola is called the vertex. The vertex is always the lowest point on the graph or the highest point on the graph of a parabola. So again, if it opens upward, we're going to have a minimum value at the vertex, and the axis of symmetry cuts it in half. And likewise, if it opens downward. Now, there's a couple ways of writing these. Okay, so here we have, compared to the basic graph, we can write x squared. The graph of any quadratic function can be written in this form, where it's either going to be a horizontal translation with a possible vertical translation, and also either a vertical stretch or compression. Okay, so again, just like we talked about last chapter. So if a is positive, it opens upward, right? If it's negative, it opens downward. If the absolute value of a is greater than 1, it's going to be a vertical stretch, so it becomes narrower. And if it's vertically shrunk or compressed, it'll become wider. Okay, so if it's between 0 and 1. And then, of course, this is a horizontal shift. Okay, if h is positive, it's going to go h units to the right. If it's negative, it's going to be h units to the left. And then, of course, this is a vertical shift. So if it's positive, it's k units up. If it's negative, it's going k units down. Okay, so if we look at this, okay, we can graph this to give the domain range by plotting points, right? So we just pick points on the x-axis and we just plot the points, and then we sketch the curve, right? So we find the axis, we just start plotting points like at negative 1, 0, 1, 2, 3, 4, and 5. So we plot these points and we get the basic shape of the parabola. Okay? And we see that the vertex is at 2, negative 6. And we also see that the y-intercept is at negative 2, 0, negative 2, 0, negative 2. And then also we know, since it goes through, this is the vertex, then we know the axis symmetry has to be at the value of x equals 2, is the axis symmetry. Okay? So the domain from the graph is going to be all real numbers, and the range is going to be what? From negative 6 to infinity. Okay? Now, again, for each graph, we're going to give the domain and the range. So here we have g. G is negative 1/2 x squared. So it opens downward, so it's got to be this one right here. Okay, negative 1/2 x squared. Okay. And we're going to compare to x squared and x 1/2. So notice this is the reflection of this one, right? And it's a little bit shrunk than x squared. Okay? So the domain of this one is, again, all real numbers in the x direction, and it's going to be from 0 to negative infinity, right? So it's going to be negative infinity to 0 for the range. Okay. Okay, what about this one? Graph each function and compare it to domain and range of this, and compare it to the graph in part B. Okay, so we got that one, part A. So part B, we got that one. Okay, so there's what we have, part B. Okay, so now what do we got here? Well, here we've got negative 1/2 x, but now what are we doing? Well, now we're taking this graph, right, and we're translating it. We're translating what? 4 units to the right, and then 3 units up. So we're going 4 units to the right and 3 units up. And so all the points on this graph are being moved to this graph. Okay? So capital F of x is just a translation of g of x. So the domain, again, looking at this graph, is all real numbers. And this time, it's going to go from what? 3 to negative infinity, or negative infinity to 3, if you will. And the x symmetry is at x equals what? 4. Now, what about this one? Now we're going to look at completing the square. What if we're given a quadratic like this, and we want to find the largest open interval over which the function is increasing or decreasing? Okay, so notice that the leading coefficient is 1. We'll start with that. And so now what we're going to do is we want to express this in this form. Okay, and we're going to do it by completing the square. So what we do is we're going to isolate the 7 from the rest of the terms. And then this is the piece we're going to complete the square with. So we're going to look at the middle term, and how do we complete the square? Well, one of the things that we remember about a square, it's going to be x plus some number quantity squared, right? So we know that when we factor it, the middle term is double whatever this term and this term, right? So we're going to take this term, take the square root of this term, and we're going to take the square root of this term, whatever this term is, and we know that it has to be double what this term is. Well, there's the x. Well, what if we take half of this, right? Work backwards. Well, if we take half of 6, we get -3. Huh. Well, that tells us that this has to be -3. Okay, but we have to square it. What? This is -3 squared. So 9 is going to be our answer here. And it makes sense because if we take x minus 3 and square the whole thing, we're going to get x squared minus 6x plus 9. Okay, and so that's the idea behind completing the square. We've got to find this thing here, whatever this term is, so that this can be factored as a perfect square. And so remember, we know that one of the things that we talked about before, oh come on now, is that if we have a plus b quantity squared, that it has to equal a squared plus okay. So a, b, there we go. So we know this form is always going to be true. A plus b quantity squared, so that if we have this a sum of a and b, so this squared, this perfect square is going to be a squared plus 2 times ab plus b. So all we have to do is work backwards and see, okay, what needs to be here in order to get this? Well, all we have to do is go backwards. Divide by 2, right? So x is always going to be one of these, right? So all we have to do is take this term here and divide by 2 and square it, and we get the number we need. But whatever we add over here, we have to also add over here. So just be careful with that. Okay, so now let's go back. So what do? We take half of -6, square it, we get -3 squared, and we get 9. So we're going to add 9 over here and add 9 here, or excuse me, I'm sorry. We're going to add 9 here and subtract 9 over here, because remember, we got to have the net effect be 0. Okay, so if we're going to add 9 to this part here, we also have to subtract 9 over here. This will be our completed square. This will be our perfect square, and then we'll just have a constant over here to deal with. Okay, so there we go. We added 9 and we subtracted 9. So then we're going to group these together and group these constants together. And now this becomes our perfect square, which is x minus 3, quantity squared. So we get x minus 3 quantity squared minus 2 from here. And now we've got it in the translated form, right? So now it's a translation of our basic function. And so now we know that the vertex is going to be located at what? HK. So this is going to be what? 3. So it's x minus h plus k. It's always x minus h plus k. If you look at going back, x minus h plus k. So when we're doing that, we want to make sure we have it in that form. X minus h plus negative 2. So that means 3 comma negative 2 is the vertex of the parabola, and the axis of symmetry goes through x equals 3. Now, find additional ordered pairs to satisfy the equation. Use symmetry about the x-axis of the parabola to find other ordered pairs, connect, and to obtain the graph. Okay, so there's different ways of doing this, right? So we got the vertex. We could have found the x-intercepts, right? And or we find the y-intercept. Okay, so the y-intercept's easy. When x is 0, we always get the constant term. So it's going to be 0 comma c, in this case 7. So now, using the symmetry, we know that this is 3 units from the axis of symmetry. So that means we're going to be 3 units over here at 7. So it's going to be 7 here and 7 here. So now this point is going to be what? 6 comma 7. Okay? And then we can also plot these points, right? So as long as we plot 3 or 4 or 5 points, we can sketch a good graph. So the domain is all real numbers. Notice a pattern for all parabolas, right? All polynomials, the domain is always going to be all real numbers. The range in this case is from -2 to positive infinity. The lowest point is the vertex at 3 comma -2, and this is going to be decreasing from -infinity to 3, and then it's increasing from 3 to positive infinity. Okay. Now, in example 2, we added and subtracted 9 on the same side of the equation, okay, to complete the square. Now, this differs from adding the same number to each side of the equation, but it's the same thing. Okay, so as when we completed the square in 1.4, what we did was we added the same thing to both sides of the equal sign. But that's the same thing as if you add and subtract the same number on the same side of the equation. Okay, it's 6 half a dozen of the other. Either you have to add and subtract the same thing on one side, or you have to add the same thing to both sides, or subtract the same thing from both sides of the equation to keep it balanced. Okay. So let's look at this one. Let's identify the intercepts of the graph. Now, right away, we know the intercept, the y-intercept, is going to be at what? 0 comma 1, right? Now, finding the other intercepts, the x-intercepts, we're going to have to kind of factor this thing out, or rewrite it in an easier to see form. Okay, so we're going to complete the square. So, but to complete the square, remember, our leading coefficient has to be 1. So we're going to have to divide everything by -3. And there's nothing, we can't factor out a -3 because these aren't multiples of 3. So we're just going to divide everything by -3. We'll have some fractions, but that's okay. So we get -3 out here. And then what happens is we're going to get 1. So there's our leading coefficient. Then this is going to be 2/3. And then we're going to have plus 1. Now, notice that here they have positive 1 here. Okay? So they factored out -3 from the first 2 terms. You're going to find there's more than one way to do this, but let's just go with what they're doing. So they're isolating the 1, and then they're factoring this. Okay? But notice what's going to happen. You're going to end up doing the exact same thing. So whether you, anyway. So they're isolating the constant term first, and then they're going to divide or factor out a -3, or divide by 3. It's the same thing. So factoring out a -3, you're going to end up with 1, and then you're going to end up with 2/3 here. Okay, and this is going to become positive. This is going to become positive. Okay, and there's your plus 1. And now what you're going to have to do is now you're going to complete the square. So in order to complete the square, what do you have to do? You have to divide this by 2, which gives you 1/3, and then square it, which gives you 1/9. So you're going to add and subtract 1/9 here. Okay, so now what are you going to do? Well, now you're going to split this off, but you're going to have to distribute this 3. Because now it's going to be -3 times this whole thing minus -3 times 1/9. Okay? And so you're going to have to distribute -3 here and then the -3 here. So again, be careful here. Okay? So this is -3 times the -1, which is going to be a plus 1/3. Okay? And so 1/3 plus 1 gives you 4/3. Okay, because this is 3/3 plus 1/3 gives you 4/3. And so now what happens? Now this is a perfect square, and you get -3 times what? Well, it's going to be 1/3. So x plus 1/3 quantity squared plus your 4/3 left over. Okay, now you've got it in the form you need it. Okay, so now now we got to find the intercepts. So obviously, if this is 0, you're going to get 1. Okay. So if this is 0, you're going to get 1, -1. Okay. Actually, it's going to be 1/3, -1/3, and then you're going to get 1 here. Okay. So the vertex, again, looking at this form, this is going to be minus, so this is going to be -1/3, comma, 4/3. So this is the vertex. So the axis symmetry is located at x equals -1/3. Okay. Now the intercepts are good additional points to find. The y-intercept is found by just evaluating f equal to 0, or f of 0. Now in this case here, you're going to get 1, right? Because this is just going to be -3 times 0 squared plus 2 times 0 equals 1. Plus 1 equals 1. So that's easy to get because all you have to do is plug 0 in here and you've got 1. So you got 0, 1, and then you use the axis of symmetry to get another point. Okay? Now, the x-intercepts are found by setting f of x equal to 0 and then solving for x. Now, in this case here, well, when we do this, we can what? Multiply by -1, right? So we want the leading coefficient to be positive. So we get this. It's not going to change anything over here. And then we're going to factor. So when we factor using the AC method, or whatever method you want to use, if you want to use the guess and check method, you're going to end up with these two factors. And now we know that one of the x-intercepts is going to be located at x equals -1, and the other one is going to be located at 1/3. Using the zero factor property, or the zero product principle. And so the x-intercepts are at 0, excuse me, yeah, no, 1/3, 0, and -1, 0. And so we've got this intercept, which will also give us this one by the axis symmetry. So we could actually get another point here. And then we got the two x-intercepts, and that's really all we need. So 5 points is more than enough to sketch the graph of the parabola. Okay. So again, so using this form and then using this form, we can graph it very easily. Okay, so the quadratic function ax squared plus bx plus c can be written in this form for a not equal to 0. And now here, h is equal to -b over 2a. And k is equal to f of h. So we can use this form and we can find h and k, or we can use the formula to find h and then just plug that in for the function to find k, which gives us another way of finding the vertex, which is the vertex formula. Now, the graph of f has the following characteristics. The parabola, it is a parabola with a vertex hk, and the vertical line x equals h is the axis of symmetry. It opens up if a is positive, opens down if a is negative. It is wider than the graph of x squared if the absolute value of a is less than 1, and narrower if it's greater than 1. Okay? The y-intercept is always equal to c, so f of 0 is equal to c. The x-intercepts are found by solving the equation this equal to 0. Okay, now if you can factor this, then that's fine. But if you can't factor it, then we have to use the quadratic formula. And notice that if this is 0, then we only got what? We're only going to have one. We're going to be at the intercept. If the determinant here, okay, or not the determinant, the oh, I forgot what you call that. It's not the determinant. It's the oh, it'll come to me. But when this is equal to 0, then the x-intercept is going to be this, comma 0. So this is going to be the vertex. It's going to be at the vertex. If it's positive, then you're going to have two intercepts, x-intercepts, and it's going to be this. And if it's less than 0, then you're going to have no x-intercepts because you can't have a negative under the radical here. So this value here under the radical will tell you whether you have two intercepts, two x-intercepts, one x-intercept, which will be at the vertex, or if there's no x-intercepts. It doesn't cross the x-axis at all. So in this here, it says using the vertex formula, we're going to find the axis and the vertex of the parabola using this equation. So our a, so first of all, a is 2, b is 4, and c is 5. And notice that our standard form has plus signs. Okay, so this is going to be 2, 4, and 5 are your a, b, and c. Okay, so now we're going to use the vertex formula, which is going to be x is equal to negative b over 2a. So b is 4, a is 2, so you just plug and chug and you get negative 1. So x is equal to negative 1. And so to find the y value, we just plug in negative 1 into here. So this is going to be 2 minus 4 plus 5, which is going to give us a 3. And so our vertex is at negative 1, comma 3. So now, if irresistance is neglected, so we can use this to model things like, for example, the trajectory or the speed or height of an object. So if irresistance is neglected, the height s in feet of an object projected directly upward from its initial height of s sub 0, right? So that could be at ground level, which is 0, or it could be at some other height. With an initial velocity of v naught, so we have s naught and v naught per second, is given by this function, this equation. So s with respect to time, so s of t is equal to negative 16 times t squared plus the initial velocity times t plus the initial height. Okay, t is the number of seconds after the object is projected, and this gives the trajectory of the object going up and down. So a ball is projected directly upward from an initial height of 100 feet with an initial velocity of 80 feet per second. Give the function that describes the height of the ball in terms of t. So all we're going to do is we're going to use this function here, and we're going to plug in for the initial velocity and the initial height, and we're done. So the initial velocity is 80 feet per second, initial height is 100, and so using those two values and plug it into our function, this is the function that describes the height of the ball over time. And then B, it says, after how many seconds does the projectile reach its maximum height? Well, that means we're going to have to find the vertex, right? And then what is the maximum height? So if we find the vertex, then that's going to give us both answers. So here we can use the vertex formula. So A is negative 16, B is 80, and so the vertex formula gives us negative B over 2A, and so we plug in our values, and we find 2.5. So X, in this case T, which is time, 2.5 seconds. So the maximum height of the ball occurs 2.5 seconds after the object is launched. Okay. Now, all we have to do now is plug in the 2.5 into our function to find what was the maximum height. And so the maximum height was 200 feet. And again, that occurred 2.5 seconds after launch, after it was launched. Now, C says, for what interval of time is the height of the ball greater than 160 feet? So here's what we're going to do. We're going to find out. Okay, so first of all, we know that the ball was projected upward. So it's going to pass 160 feet. If it's going to pass 160 feet, it's going to pass it one time, but then the ball's going to stop and it's going to come back down, so it'll hit 160 feet at most at 2 spots. Okay, so here's where we need to find where it is greater than 160 feet. So it's going to be an inequality, right? So we're going to solve this inequality here. So all we're going to do is we're going to see what we can do on this side, okay? And what we're going to do is we want to subtract 160 from both sides. And so we get this. And so now we want to find out where it's greater than 0 based on this quadratic. And so now what we're going to do is we're going to see if we can factor out anything else. We can definitely factor out a 2, right, because they're all even. So we want to try to factor out a common factor as much as possible. And so there is a common factor of 4. Okay, so we can actually divide both sides by negative 4 to make this positive. And so you get this. Okay, so whatever the solution is for this one will also be the solution to this one. Okay, so now by the quadratic formula, we find this. We find that t is equal to 0.92 seconds, and we also get t is equal to 4.08 seconds. Okay, so that means that at t equals this number and t equals this time, that's when the ball was at 160 feet. So that means the ball was greater than 160 feet between these two values. Okay? Now, you can test it too. Okay, and it's easy to test. All you have to do is find out the value of the function in this interval, right? So you have an interval from negative infinity to 0.92. Then you've got the interval between 0.92 and 4.08. And then you've got the interval from 4.808 seconds to infinity. And so what we can do is we can test a value in between each one of these, and that value will be either positive or negative. Okay? And if it's positive, then it's going to be greater than 0, right? If it's negative, it's less than 0. So we want to find out where it's greater than 0. And so we'll find out that the ball is more than 160 feet between those two values, which is what I had reasoned before. Okay? But again, when in doubt, use a test point. After how many seconds will the ball hit the ground? Well, if it took 2.5 seconds for it to reach its maximum height, and again, we're neglecting air resistance, so it'll take the same amount of time to come back down and hit the ground, so it's going to be a total of 5 seconds. But we can always check by finding out when is the height 0. And again, we're going to get 2 times. We're going to get t is equal to 0, and I bet you the other t is going to be 5. So again, we use the quadratic formula in this case, and we simplify. And look at that. We get negative 1.04. Now, why did we get 6.04 here? Oh, I know why. Because this is when it started, right at 0. Okay? But this doesn't make any sense because remember, we were 100 feet, right? We were 100 feet above the ground already. Okay, so I forgot about that. So again, I was assuming 0. So that's another thing why you always want to use the formula, because it will always make sure you get the right answer. But was it 2.5? I think it was, hold on a second. Where was it? Yeah, 2.5. So it reached 2.5, maximum height 2.5 seconds, but I forgot that it was 100 feet off the ground. So it's going to be in the air for a little bit more than another 2.5 seconds after maximum height. Okay. Hold on a second here. I want to get back to where it was. Okay. And so, again, why do we mark this up? Well, because we can't have negative time. Okay. Remember, t equals 0 is it was at 100 feet, and that's where it was launched. And so this number is the correct answer. This is when the ball hit the ground. So it hit the ground after approximately 6.04 seconds. Okay, so now here we give a table, right? So we have a year and the number of visits. So this is the number of hospital outpatient visits in millions for selected years shown in this table. So for all of the years, okay, and the table 99 represents 1999. So these are years after 1900, okay, and 100 represents 2000, and so on and so forth. Okay, so this is number of years after 1900. Okay, so these are the number of visits, outpatient visits in millions. Okay, so we're going to use this table to see what we can find and what we can learn. So what we're going to do is we're going to prepare a scatter plot. Anytime we have data and we're trying to figure out the relationship between two variables, we're going to use a scatter plot, and we're going to determine if a quadratic model is appropriate. Okay, and then we're going to use quadratic regression, okay, that we talked about before in 2.5. And we can use a graphing calculator to do that, okay? Now, if we look at this, okay, if you look at this data here, okay, the scatter plot suggests a quadratic function with a negative value, okay? So it's got a slight curve down, so there is a slight curve here, okay? Some people might look at this and say it's linear, but it does seem like there's a curve here, and it does seem like it's downward, okay? So now, if we use our quadratic regression, which is under quad reg on the calculator, so what you would do is you'd go to distribution, so you'd go to second vars, and you'd pick quad reg, and quad reg is going to be the one you're going to use to model or figure out the best fit model for the data. And so if you do that, you're going to come up with this regression model. Okay, and what it's going to do is going to give you your A, B, and C. So here's your quadratic equation, your quadratic function, and it's going to give you your A, B, and C. So you just have to write it out with the A, B, and C inputted. Okay. Now use the model from part A to predict what it would be in 2016. So that's going to be what? That's going to be 116 years after 1900. Okay, so X is going to be 116. So all you have to do is put 116 into the calculator, okay, and or use the stat calc option, or excuse me, second calc option for your window, and then use the value right? You're looking for a value and then just stick in 116 for x and it'll give you approximately 122 million, okay? Or just stick 116 into the function and just simplify it. Just plug and chug and you're going to get approximately 822 million outpatients visits that year. Okay, so that is the end of this section. Again, please make sure you go through these examples, make sure you understand them, make sure you write down any questions. If you get stuck, review or bring those to class. Do the other examples that are in the textbook. Practice with the suggested homework, and again, make sure you come to class prepared. Okay, so until then, have a great day, and I'll talk to you next time.